Greetings of the day to all of you. Today I am going to discuss with you the last type of series reactive compensator, which is called SSSC. Okay, in our last 2 to 3 lectures, or around 3 to 4 lectures, I have been discussing with you the other types of series compensators, which are thyristor based. Actually, these series compensators are categorized like this. Just like shunt compensators, these series compensators are categorized on the basis of the the devices used or the type of equipment used. For example, we have thyristor based series compensators. This is one category of series compensators. And another category of series compensators is converter based series compensators. Converter based series compensators. This classification is done in the same way as we have done in case of shunt compensators. For example, in case of shunt compensators, we have thyristor based shunt compensator like SVC, and we have converter based shunt compensator like STATCOM. Similarly, series compensators are also classified on the basis of thyristor based series compensators and converter based series compensators. Thyristor based series compensators we have already discussed, like GCSC, that is GTO controlled series compensator or GTO controlled series capacitor. The second type of thyristor based series compensator discussed by us was TSSC, that is thyristor switched series capacitor. And the third type of series compensator, which was discussed by us and concluded in the last lecture, was TCSC, that is thyristor controlled series compensator. So GCSC, TSSC and TCSC, these are the three types of thyristor based series compensators. And as far as converter based series compensator is concerned, we have only one type of converter based series compensator, that is SSSC, that is static synchronous series compensator. Right. Today I am going to discuss with you about this converter based series compensator, SSSC. I will write here static synchronous series compensator. And its acronym is SSSC. SSSC means static synchronous series compensator. Actually, first of all, I will give you the definition of this SSSC. There is a global definition or universal definition of SSSC, which is given by two agencies. One is IEEE and another is CIGRE, CIGRA. I hope you already know about IEEE. I don't know how many of you know about this organization. IEEE, you know, it is its full form is Institute of Electrical and Electronics Engineers. Institute of Electrical and Electronics Engineers, IEEE. This is one organization or one agency. It was founded in the year 1884. It was founded, I will write here, in 1884, way back in 1884. At that time, it was called American Institute of Electrical Engineers, AIEE, and then it was renamed as IEEE, in 1963. In 1963, it was renamed as IEEE. Okay. Another organization is CIGRA, CIGRE. It's a French name, and its full form is, in French language, it is called Conseil International des Grands Recherches Electriques This is the French name. C for Conseil, I for International, D, G for Grants, R for Receipts, and E for Electrics. Conseil International des Grants Receipts Electrics is the French name, and its English name is International Council for Large Electric Systems. Large Electric Systems. This is its English name, and it was founded in the year 1921. So these are two leading organizations in electrical and electronics engineering. One is IEEE and another is SIGRE. And these two organizations, that's IEEE and SIGRE, have given a definition of static series synchronous compensator. According to these two organizations, SSSC is the series reactive compensation scheme. Is the series reactive compensation scheme using switching power converter as a synchronous voltage source to produce a controllable voltage in quadrature with line current. Let me write it. SSSC, as per IEEE and SIGRE, is defined as SSSC is the series reactive compensation scheme. Series reactive compensation scheme using a switching power converter. It does not use thyristors, it uses converter. Switching, using a switching power converter as a synchronous voltage source. As a synchronous voltage source to produce a controllable voltage in quadrature with line current. You know, all series compensators actually produce voltage, whereas we already know that shunt compensators, they inject the current. Whereas shunt compensators inject the current, series compensators inject the voltage. Since SSSC is a series compensator, it is a series reactive compensation scheme using a switching power converter as a synchronous voltage source to produce a controllable voltage in quadrature with line current. So for example, if this is your transmission line, and you know, in series with this transmission line, you inject some voltage, say VQ, maybe through a transformer, an injection transformer, which is connected to your SSSC. This is your SSSC. The SSSC produces a voltage, and then that voltage is injected. So that means your SSSC acts as a voltage source, which is called synchronous voltage source. It produces a controllable voltage. This is controllable voltage, VQ, in quadrature with current. That means if this is the current, the voltage may be out of phase with current by 90 degrees, or the voltage VQ may be lagging behind the current by 90 degrees, or it may be leading the current by 90 degrees, like this, depending upon how do you use it, whether you use it as a capacitive reactance or as an inductive reactance. So this VQ is always in quadrature with line current, transmission line current at 90 degrees always. So therefore, as per IEEE and SIGRE definition, SSSC is nothing but it is a series reactive compensation scheme using a switching power converter as a synchronous voltage source to produce a controllable voltage in quadrature with line current. Let us see how it produces the voltage which is injected in series with the transmission line and which is in quadrature, that is at 90 degrees with the line current. Now, as far as this voltage source, static synchronous series compensator actually uses a voltage source inverter. Okay. As far as this voltage source inverter, or what we call as voltage source converter, is concerned, it acts as a synchronous voltage source. Synchronous voltage source. SVS. When I say it acts as a synchronous voltage source, that means this voltage source converter has DC side and AC side. On its DC side, for example, this is the voltage source converter. It has a DC link, DC side, and this is the AC side. it converts this DC power into AC power, okay? So therefore it acts as a synchronous voltage source, producing three-phase set of voltages. So it acts as a synchronous voltage source, just like an ideal synchronous generator. What does your synchronous generator do? It produces a set of three-phase voltages. So similarly, your inverter also can convert DC into AC, and it can produce a set of three-phase voltages. Okay, and hence it, just like an ideal synchronous generator, it acts as a voltage source, and it is called synchronous voltage source. So therefore it produces three-phase AC voltages at fundamental frequency of controllable amplitude and phase angle. I mean, these voltages, the voltage which it produces, it has controllable amplitude and controllable, you can control its phase angle also. Okay, and we can make this voltage source converter to absorb the reactive power or to inject the reactive power, and we can make it to absorb the active power or deliver the active power. However, for delivering the active power, there should be some energy storage like battery bank or superconducting magnetic energy storage or fuel cell or supercapacitor, etc. at its DC bus, so that it can take energy from that storage, energy storage, and supply that energy in the form of AC power to the bus to which it is connected. So therefore this voltage source converter, which is used in this static synchronous series compensator SSSC, because SSSC is actually a voltage source converter. This voltage source converter, when it is used as an SSSC, it acts as a synchronous voltage source. It produces three-phase AC voltages of controllable amplitude and controllable phase angle. It can absorb reactive power or it can supply reactive power, and it can absorb active power or supply active power as well. However, for supplying the active power, it must have an energy storage at the DC bus. So it looks like this. The SSSC is connected in the system like this. This is the transmission line, and this is the transmission line current. Then I have an injection transformer like this, or this is also called coupling transformer. You can call it coupling or injection transformer. Coupling oblique injection transformer. If you move top to down, it is a step down transformer. If you move bottom to top, it is a step up transformer. Okay, fine. Then we have a voltage source converter like this. This is the voltage source converter, and symbolically a voltage source converter is shown like this. This is voltage source converter, which acts as SSSC, static synchronous series compensator. And then it has a DC bus with DC bus capacitance CDC, and say for example DC bus voltage VDC, right? And we may have energy storage also there. This is like a battery bank, etc. This is energy storage. However, this energy storage is optional. Optional means only when you want to supply or deliver active power to the transmission line or to the transmission bus, then only at the DC bus we will have energy storage. Otherwise, if you want only a reactive power control, then only DC bus capacitor is required, no energy storage is required. Fine. Then we have a controller here. Okay, we have a control scheme here, and to this control scheme we have two references: QREF, that's reactive power control, reference reactive power, and PREF, that is reference active power. And this is the control signal which controls the switching of the switches of power converter. QREF is the reference reactive power and PREF is the reference active power. So therefore active reactive power control in both the directions can be done by this SSSC. I mean, it can inject the reactive power or it can absorb the reactive power. Similarly, if it has an energy storage at its DC bus, then it can do the active power exchange also. I mean, it can absorb or draw the active power from the transmission bus, or it can supply active power in series with the transmission bus. And across this transformer secondary, there is a voltage VQ, which is of controllable magnitude. Okay, so that's it. This is how a static synchronous series compensator SSSC is connected in the system. Now this, as far as QREF and PREF are concerned, this reference reactive power, QREF basically controls the, say for example, the bus voltage is here V, and inverter output voltage is V0. It controls the magnitude or amplitude of inverter output, three-phase output voltage V0 for reactive power control. And this reference, that active power reference active power, Pref, it controls the phase angle of the inverter output voltage. As you have studied in a STATCOM, actually injects the current, whereas this SSSC injects the voltage. So therefore this is a, see, you can see it injects voltage in series with the transmission line. Whereas you have studied about the STATCOM injects current in parallel with that transmission bus. So that is a shunt compensator, this is a series compensator. Anyway, we have seen in case of a STATCOM also, by controlling the magnitude or amplitude of STATCOM inverter output voltage, reactive power control can be achieved. And by controlling the phase angle of STATCOM inverter output voltage, active power exchange can be achieved. We have already studied that in case of a STATCOM. Same thing can be achieved with the help of the series compensator, SSSC, by controlling the SSSC inverter output voltage amplitude, which will be done by this QREF signal. The reactive power control can be achieved. I mean, it can either inject the reactive power or it can absorb the reactive power. Similarly, with the help of this reference active power signal, this PREF, the phase angle of inverter output voltage V0 is controlled. And by controlling the phase angle of inverter output voltage, active power exchange can also be controlled. I mean, it can either deliver the active power or it can draw the active power, right? So if you want to use this SSSC exclusively for reactive power control only, and you don't want any active power control, you want active power 0, you want only reactive power control, then in that case this PREF signal has to be set to 0. This will be equal to 0, only QREF will be there. Fine. Now, in order to understand the operation of SSSC, let me tell you this SSSC, I mean, if it is acting as it can act as a capacitive reactance or as an inductive reactance, variable capacitive reactance or as a variable inductive reactance, just like TCSC, which we have concluded in previous lecture. Just like thyristor controlled series compensator, which can act as a variable capacitive reactance or a variable inductive reactance, SSSC, which is a converter based series compensator, can also act as a variable capacitive reactance or as a variable inductive reactance. In order to understand its working or its operation as a variable capacitive reactance, I can say that it acts just like a series capacitive compensation. So it is analogous to, its operation is analogous to series capacitive compensation. Series capacitive compensation. And we have, if you remember, we have already studied about series capacitive compensation, probably in module 1 or module 2. Okay, series capacitive compensation looks like this. You have sending end voltage, for example, and you have, this is the transmission line reactance JX, okay, or JXL, and this is JXC, right? And then we have receiving end voltage. For example, this for a two machine model, this is sending end voltage Vs, this is receiving end voltage Vr. This is the actual transmission line reactance. And in case of a series capacitive compensation, what we do, we place a capacitor in series with the transmission line. This the voltage across this inductive reactance or transmission line reactance is, for example, VL. And when we put capacitor in series with this, and if the current is in this direction, it controls, say, this is the flow of power, for example. Now, suppose power is flowing from sending end to receiving end. The current will be in this direction. This current results in the voltage across the transmission line, which is VL. And this current, when flowing through this capacitive reactance, will cause a voltage across capacitive reactance, which is VC, like this. Okay. So as you already know, when we put a capacitor in series with the inductor, in series with the transmission line, What it does, it reduces the overall reactance of the transmission line. And we know that for an uncompensated transmission line, P is equal to V square by X sine delta. This is for uncompensated transmission line. Uncompensated line. And for a series capacitive compensated line, this power gets modified to, it is V square by XL minus XC sine delta. Where what is now transmission line reactance? Here it was V square by XL, uncompensated line, and now this is series compensated line. By placing a capacitor in series with the transmission line, the net reactance of the line becomes now XL minus XC, so it decreases. When it decreases, the power flow capability of the transmission line increases. We already know it, okay? Or this P is also given by P is equal to V square by KX sine delta. Well, what is K? K is XC by X. Okay, it's XC by XL. Right? So, it is what is K? K is XC by XL, and it is called degree of series compensation. Degree of series compensation. Okay. Anyway, whenever we do the series capacitive compensation of a transmission line like this, the power equation gets modified. The overall line reactance decreases. It was for uncompensated line, it was XL and higher value, and it gets reduced by XL minus XC. So it reduces the power transferring capability of the transmission line, increases. This is how compensation is done. The same thing can be explained with the help of a phasor diagram. For example, if you draw the phasor diagram, this is sending end voltage Vs, this is receiving end voltage Vr, right? Now, if compensation is not done, then your transmission line voltage, transmission line reactance voltage is VL, fine. But when you do the series capacitive compensation, the voltage across capacitor, VC, where the current flows through the capacitor, the voltage across capacitor is I into JXC, which is equal to VC, and it is opposite to this. So therefore, what the capacitor does, it produces a voltage VC like this. So therefore, what happens to the total voltage? If you see in terms of voltage, not in terms of impedance, line reactance or line impedance, the total voltage, transmission line voltage, is not now VL, it's VL plus VC. So therefore, your VL now increases. If I call this VL as the voltage across the transmission line, it increases by a factor of VC, where VC is the voltage across series capacitor. Without series capacitor, your transmission line voltage is only up to this point, VL. But with series capacitor, this voltage VC increases the overall voltage across the transmission line, which is now VL. Let me call this VL dash. And what is this VL dash? It is VL plus VC. So it increases. It is this VL dash is greater than VL. So obviously, when the series capacitive compensation, when it increases the voltage across the transmission line, so current also increases. And when current increases, the transmittable power or power transmitted over the line also increases. So this is how we explain it in terms of phasor diagram. So there are 2 points of view. We can understand this series capacitive compensation either from the point of view of transmission line reactance or from the point of view of voltage across transmission line. From the point of view of voltage across transmission line, the overall voltage across transmission line grows. It is greater than that of uncompensated line. It becomes greater by a factor of VC, where VC is the capacitive voltage or voltage across the series capacitor. And as the voltage increases, current increases. As current increases, the power transmitted over the line also increases. In terms of line reactance, the power equation becomes V square by XL minus XC sine delta. So therefore, overall reactance is not XL, it is XL minus XC. So line reactance, effective line reactance decreases, so transmittable power increases. So this is how a capacitive, series capacitive compensation works. So similarly, in a similar way, if we replace this capacitor by synchronous static synchronous series compensator, which is basically a voltage source inverter. That voltage source inverter acts as a synchronous voltage source, and that SSSC works in the same way as series capacitive compensation, of course with some differences that I'm going to discuss with you. So therefore, in a similar way, by producing or by providing a synchronous voltage source with SSSC converter, now our system becomes like this. Again, this is sending end voltage. Now, instead of having capacitor, I have voltage injected voltage in series with the transmission line. And who injects this voltage in series with transmission line? SSSC. Because SSSC is a voltage source inverter. It produces a three-phase voltage. It acts as a synchronous voltage source, and it provides a voltage, for example, VQ in series with the transmission line. That's it. And transmission line reactance is JXL, and voltage across this transmission line reactance is VL. We already know it. And this is the receiving end voltage. Let us assume that power is flowing from sending end voltage, sending end to receiving end. So this is your sending end voltage Vs, this is receiving end voltage Vr. So we are replacing capacitor by injected voltage. How much voltage is injected in series? This much. And it is injected by synchronous voltage source, or it acts like a synchronous voltage source. It is actually the voltage produced by the SSSC inverter. Okay, and that voltage is injected in series with the transmission line with the help of this injection transformer. This is SSSC converter, which converts DC into AC voltage, and with the help of this injection or coupling transformer, it is injecting a voltage VQ in series with the transmission line. So this VQ is the injected voltage by SSSC. Okay, now again you can look at it from the point of view of line reactance. What happens to the overall line reactance? That decreases. Again, I will write for uncompensated transmission line, the power delivered or power transmitted over the line is V square by X sine delta. I will again write within the brackets that it is for uncompensated transmission line, uncompensated line. And for line compensated by SSSC, the power equation gets modified to P is equal to V square, let's call this XL, V square by XL minus VQ by I sine delta. Because what is the reactance? Reactance of the transmission line is XL, and when a voltage VQ is injected in series with the transmission line, it acts as a reactance. And what is the reactance? Reactance of the synchronous voltage source. It is the injected voltage divided by the current, and how much current is flowing in series with the transmission line? I. So VQ by I is the reactance, and this reactance subtracts from this reactance, so overall reactance decreases. Now you can see for uncompensated transmission line, line reactance is XL, and it determines how much power will be transferred over the line. And with series compensation by SSSC, the line reactance is reduced by a factor of VQ by I, where VQ is the injected voltage by SSSC. So now line reactance is XL minus VQ by I. It reduces by a factor of VQ by I. So as the line reactance, effective line reactance reduces, the power transmitted over the line PQ, or let us call this P, it increases. So therefore, the series compensation is done by this SSSC by injecting a voltage in series with the transmission line, and it can increase the power transferable over the line, or transmittable power over the line. This is how we look at it from the point of view of line reactance, effective line reactance. From the point of view of phasor diagram, or from the point of view of effective voltage across the transmission line, it is like this. So for example, this is sending end voltage Vs, this is receiving end voltage Vr, this is the transmission angle delta. And we already know that, for uncompensated line, what is the voltage across line reactance? It is VL. But since you are using SSSC converter, and this SSSC converter injects a voltage VQ in series with the transmission line, this is the injected voltage. So therefore, what becomes now overall voltage across the line? It is not VL, it is VL dash equal to VL plus VQ, because they are in the same direction. So effective voltage VL dash increases, and you can see this VL dash is greater than actual line reactance, transmission reactance voltage VL. So therefore, this voltage injected by SSSC increases the effective voltage across transmission line, and as effective voltage across transmission line increases, that increases the current through the transmission line, and hence that increases that transmittable power over the transmission line. This is how we look at it. So therefore, equivalently, we can say that if we draw the comparison between SSSC and series capacitive compensation, they look like same. I mean, series capacitive compensation also increases the, it does the series compensation, it increases the power transmitted over the line. SSSC also acts as a series compensation, and it injects the voltage in series with the transmission line, and it increases the power transfer capability of the line. It does the series compensation. So therefore, the injected voltage can be written as voltage across capacitor. I mean, if you consider the two compensations similar, like this capacitive compensation and this synchronous voltage compensation, if you compare them similar, this is VL, VC, this is VL, and this is VQ. If you draw the comparison between the two, they behave similarly. So this injected voltage is same as capacitor voltage, and that is equal to minus Ji into XC. If you write this injected voltage by SSSC in terms of capacitive compensation, so what is the voltage across capacitor? VC, and that is Ji into XC, and that is equal to VQ, right? So, or we can write VQ equal to VC equal to minus Ji into K into X, where what is X, what is K? K is equal to XC by XL, and it is called the degree of series compensation. Okay, so therefore VQ can be made as a function of current. The difference between two compensation schemes is that in case of series capacitive compensation scheme, the voltage across capacitor is a function of current, because this capacitor has a fixed reactance XC, and the VC is equal to minus Ji into XC. As transmission line current increases with increase in the load on the line, VC also increases. But in case of SSSC, this VQ can be made independent of current, because this VQ is basically injected voltage and it has nothing to do with this current. Here this VC is basically the voltage drop across the capacitive reactance, and it is a function of current, as you can see from this equation. But the voltage injected by SSSC is VQ, and this voltage injected depends upon the modulation index of your SSSC converter or SSSC inverter. It is independent of transmission line current. Whatever the transmission line current is, whether it increases or decreases, VQ remains independent of current. That is the difference between the two compensations, independent of line current. So injected voltage VQ by SSSC, it is made independent of line current I, whereas in series capacitive compensation it is not independent of current. It changes with change in the current. So therefore, which is better compensation? This is better compensation, because once you decide that this much of compensation should be done, and then it should be made independent of the line current. So therefore, SSSC converter or SSSC inverter injects a voltage VQ which is independent of the line current. So this is the difference between the two types of compensations. Another thing is that when we say that VQ is injected in series with the transmission line, this VQ can be made lags behind transmission line current I by 90 degrees, and it gives capacitive compensation. Because in case of a capacitor, current leads the voltage by 90 degrees or voltage lags current by 90 degrees. So therefore, if this is your current, transmission line current, this is the voltage injected by SSSC, and if this voltage lags is incorrelated with the transmission line current, it lags behind the current by 90 degrees, or current leads the voltage by 90 degrees. So this is similar to capacitive compensation. Okay, so there is the injection of reactive power, and overall voltage of the line increases, and more power can be transferred over the line. However, with the help of this SSSC, what we can do, we can make VQ lead the current by 90 degrees. That is controllable. So if VQ leads current by 90 degrees, then it becomes inductive compensation. And that can be very easily done in this SSSC converter. That means if this is the current, transmission line current I, the injected voltage VQ can be made lead the voltage by 90 degrees. We lead the current by 90 degrees, or in other words, line current lags behind voltage by 90 degrees. And in which type of circuit element current lags behind voltage? Inductive. So therefore you can make your SSSC to work in the inductive region, whereas that is not possible with the series capacitive compensation. In case of series capacitive compensation, the capacitor voltage VC always lags current by 90 degrees, or current leads voltage by 90 degrees, so it produces only capacitive compensation. But you can make your SSSC to produce capacitive compensation if VQ lags I by 90 degrees, or by changing the phase, by reversing the phase angle of the injected voltage. By reversing the injected voltage, you can make VQ lead current by 90 degrees, and in that case it acts as an it works in the inductive region, just like TCSC. So this is something which is not possible with series capacitive compensation. Series capacitive compensation always does the capacitive, makes your compensator to work in the capacitive region. But SSSC can, by reversing the injected voltage phase, we can make SSSC to work either in the capacitive region or in the inductive region. So this is one of the major advantages of SSSC series compensator over series capacitive compensation. Okay. So obviously when VQ leads I by 90 degrees, I lags behind VQ by 90 degrees. That means अगर आपकी ये इंजेक्टेड वोल्टेज अर्लियर कैपेसिटिव में मैंने ये डायरेक्शन दिखाई थी, अब इसकी डायरेक्शन चेंज होगी VQ, और ये आपकी ट्रांसमिशन लाइन रिएक्टेंस के अक्रॉस वोल्टेज है VL. What is the effective voltage across the transmission line? If this is sending end voltage, this is receiving end voltage. Yani, if this is your, for example, sending end voltage VS, this is receiving end voltage VR, this is delta. Uncompensated line ke liye, the transmission line reactance voltage is VL. But what we are doing now, VQ jo hai, VQ is now opposing VL. So ye VQ hai, this is VQ. So therefore what is your VL dash? आपकी इफेक्टिव ट्रांसमिशन लाइन के अक्रॉस जो वोल्टेज है, दैट डिक्रीजेस बाय अ फ्रैक्शन ऑफ VQ. सो दिस इज योर VL dash, and this VL dash is less than VL. So therefore when SSSC operates in the inductive region, it decreases the effective voltage across the transmission line, and hence it decreases the current, and hence it decreases the power transmitted over the line. In terms of reactance, we can say this is in terms of voltages. In terms of reactance, we can say P is equal to V square by XL plus VQ by I sin delta. When your compensator was working in the capacitive compensation region, I had written here minus. Overall reactance kam hoti thi, P increase hota tha. But when it is operating in the inductive region, by reversing the injected voltage phase, by making I lag the voltage by 90 degrees, by operating your SSSC in the inductive region, it now becomes plus. So therefore what happens to the effective reactance? It increases, so P decreases. So hence the beauty of SSSC over the series capacitive compensation is that series capacitive compensation can only work in the capacitive region, but SSSC can be made to work in capacitive region as well as in the inductive region. So it can increase the power transmitted over the line, it can decrease the power transmitted over the transmission line also. So both are possible. We can make it a series capacitive compensator or series inductive compensator. Right. Now after this, I would like to write a generalized equation for injected voltage by SSSC. Generalized equation for injected voltage is VQ is equal to plus minus J VQ. I am writing J because this voltage is in quadrature with current. It either lags current by 90 degrees or leads current by 90 degrees. So that's why I am writing plus minus. Plus means the voltage leads current by 90 degrees. Minus means it lags the current by 90 degrees, and it is a function of some parameter, control parameter, sigma, and then I dash by I. Okay, I is the actual current in the line, I mean uncompensated line, and I dash is the current when it is compensated by this SSSC series compensator. Okay, what is this sigma? It is control parameter. It is a control parameter. Okay, and this VQ, which is a function of sigma, is magnitude of injected voltage. It represents magnitude of SSSC injected voltage. And this magnitude of injected voltage, it can vary from 0 to maximum value, VQ max. I mean, it's a variable thing. You can make it variable. You can make it vary from 0 to some maximum value, VQ max, depending upon the design. Okay, and the equation for active power over the transmission line, I have already written this. It is V square divided by XL minus VQ by I sine delta. Right? Now let us try to draw the P delta characteristics, power angle characteristics of SSSC. P delta characteristics. The equation, which I am not going to derive, you can find that from literature. Equation for power which is flowing over an SSSC compensated transmission line. It is given by P is equal to V square by X sine delta plus V by X into VQ cos delta by 2, where VQ is the injected voltage injected by this SSSC compensator. Now we can draw P delta characteristics, and we can show P as a parametric function of VQ, like this, something like this. This is delta, and this is power, PQ, which is, say for example, in per unit. This is 0, this is 0.5, this is 1.0, and this is 1.5 per unit. Similarly, on the bottom side, it is minus 0.5 per unit, and so on. For an uncompensated line, so see, this is 0, this is, for example, here, delta 90 degrees, and this is delta 180 degrees. This is for uncompensated line, which has, in which case VQ is equal to 0. We are not injecting, we may have this SSSC connected in the system, but it is off, it is in the off state, it's not injecting any voltage. So for VQ equal to 0, ये term ही आपकी 0 हो जाती है, so your P equation becomes V square by X sine delta. So this is the power angle characteristic of uncompensated transmission line. And then after this, if you if you connect your SSSC and make it to inject the voltage in series with the transmission line, your power angle characteristic is now going to change. For example, it may become something like this. This is for, say for example, VQ equal to 0.353 per unit. Injected voltages, here it is 0, here it is 0.353 per unit. And this is another power angle characteristic for VQ equal to 0.707 per unit. I have taken some numerical values arbitrarily. V equal to injected voltage equal to 0, so P power angle characteristic, uncompensated line. And then I am doing the series compensation by SSSC, and if the injected voltage is 0.353 per unit, your power angle characteristic raises, because power transmitted over the line now increases. We already know that. If VQ is now further increased from 0.353 per unit to 0.707 per unit, the power transmitted over the line further increases, and peak power increases from 1 per unit to 1.5 per unit. You can see it is 1.5 per unit. This is if you are using your SSSC in the capacitive region. If you are using your SSSC in the inductive region, what it will do, VQ, the injected voltage, its phase will be now reversed. And therefore, instead of increasing the power, it will decrease power. and your injected voltage will be negative. So for example, for VQ equal to, let me show you, this is the power angle characteristic for VQ equal to minus 0.353 per unit. See now here injected voltage is plus, here I have made it minus. Minus means now earlier for positive values the voltage was leading the injected voltage was leading the transmission line current, or if I show transmission line current like this, the injected voltage was lagging the transmission line current, or current was leading the voltage. Okay, so your SSSC was working as a in the capacitive region. It was doing capacitive, series capacitive compensation, and as VQ magnitude was increased, power transmitted over the line was increased. But in the inductive region, this VQ is now reversed. If this is I, VQ is now made to lead the current by 90 degrees, or current is made to lead VQ by 90 degrees. So that is the inductive. That means your SSSC is now injecting a reverse magnitude voltage, say for example minus 0.353, and it is operating in the inductive mode of region. And in the inductive mode of region, what happens to the power transmitted over the line? The power transmitted over the line further decreases. It is even less than uncompensated line. Okay, and you can further reduce it. Say for example, this is for VQ equal to minus 0.707. Okay, so you can further reduce it. So therefore, on the other hand, if you draw, the power angle characteristics for series capacitive compensation, delta and power is in per unit. So this, for example, this is 0.5, this is 1, and this is 1.5. This is delta equal to 90 degrees, this is delta equal to 180 degrees. This is for degree of series compensation equal to 0, uncompensated line. It is similar to this VQ equal to 0. And then let us suppose we do some series capacitive compensation, put a capacitor in series with the transmission line, and let us suppose the degree of series compensation is K is equal to 1 by 3, and it is equivalent to VQ equal to 0.353. Similar. Here peak is less than 1, here also peak is less than 1. And if we increase degree of series compensation by increasing the capacitive reactance further and make K equal to 1 by, here K is 1 by 5. Now make K equal to 1 by 3. K equal to 1 by 3 gives a peak transmitted power of 1.5 per unit, which is equivalent to VQ equal to 0.707. VQ equal to 0.707 also gives a peak transmittable power of 1.5 per unit. So this is the similarity between the two. However, the difference between the two is there are two differences between series capacitive compensation and series compensation by SSSC. Number one, in series capacitive compensation, as the degree of series compensation increases, the transmittable power increases as a percentage of power of the uncompensated line. So for example, here it may increase by 20%, then 30%, and it is dependent on alpha. Whereas in SSSC series compensation, as VQ is increased, the power transmitted over the line does not increase as a percentage, it increases as a fraction of uncompensated power, and it is independent of delta. For example, here delta equal to 0, whatever is the degree of series compensation, the transmittable power is 0, but that's not the case here. Here for delta equal to 0, and VQ equal to 0, power transmitted is 0. For VQ equal to 0.353, the power transmitted increases. For VQ equal to 0.707, power transmitted increases. So the main difference is that whereas in series capacitive compensation, with change in the degree of series compensation, with increase in the degree of series compensation, K, as it is increased, the transmittable power increases by a fixed percentage as compared to that of uncompensated line, and it is dependent on alpha, on delta. Whereas in SSSC series compensation, as VQ is increased, injected voltage is increased, the power transmitted increases as a percentage of uncompensated power and independent of delta. That is one difference. Another difference is that whereas in this series capacitive compensation can only increase the power because it it makes only capacitive compensation. But you know that SSSC can do capacitive compensation as well as inductive compensation. I mean, it can make your compensator SSSC too. We can make it work in the capacitive region as well as in the inductive region. In the capacitive region, as VQ increases, transmittable power also increases because overall effective line reactance decreases. But in the inductive region, the injected voltage is phase reversed. It is minus. Here it is plus, here it is minus. So overall line reactance increases and current and hence power transmitted decreases. So as we increase the injected voltage in the inductive region, the transmitted power decreases, which is not possible with series capacitive compensation. And another very important point with SSSC is that we can make power even negative. Negative power means normally power flows from sending end to receiving end. This is VQ and this is VL. It flows from sending end to receiving end. Say for example, this is sending end voltage, this is receiving end voltage. We show the flow of power like this. But we can make power flow to reverse. We can make it flow from receiving end to sending end. How? If this condition is fulfilled by making the magnitude of injected voltage greater than the difference between sending voltage and receiving voltage, if VQ, that's the injected voltage, is made greater than Vs minus VR mod, then power flow reverses. Power flow reverses. That means we can make power to flow from receiving end to sending end, which is not possible with series capacitive compensation. Okay, so therefore series this SSSC compensation, which is a series compensation, converter based compensation, is different from series capacitive compensation from certain points of view. Number one, in case of a series capacitive compensation, the compensator works only in the capacitive region, not in the inductive region, so that we can only increase the transmittable power over the line as the degree of series compensation increases. Because as the degree of series compensation increases, that means capacitive reactance increases, that means overall reactance of the line decreases and more power can be transmitted. However, can you make your this capacitive compensator to work in the inductive region? No. Whereas in SSSC, we can make the compensator to work in the capacitive region if the injected voltage, for example, lags behind the current by 90 degrees. Okay, and it acts just like a series capacitive compensator. But the difference is, in series capacitive compensator, the capacitive voltage is dependent on current, whereas in this case, the injected voltage is independent of current. So we can fix the injected voltage, it is independent of transmission line of current. That is one difference. Another difference is that we can make our SSSC to work in the inductive region if the voltage can be made to lead the current by 90 degrees. That means if the polarity of the voltage is reversed. Here it was this. Now if you reverse its polarity, make it negative, as I have shown here, the power, your SSSC works in the inductive region, and power, overall line reactance now increases, and transmitted power, instead of increasing, now it decreases. So this is second difference. Third difference is that in series capacitive compensation, as K is increased, the power increases as a fixed percentage of that of uncompensated line dependent on delta. Whereas in this case, as when it is operating in the capacitive region, as VQ increases, the power transmitted increases as a fixed fraction of uncompensated power, and it is independent of delta. And finally, one more advantage or flexibility of SSSC is that if this condition is met, that is, injected voltage is made greater than the difference between sending and receiving end voltage, the direction of power flow can be reversed. So although series capacitive compensation and SSSC compensators both are series compensators, now you can see that SSSC compensator, which is a this converter based compensator, it is much more flexible than the series capacitive compensator, and it can do many jobs. I mean, it can do some additional functions which cannot be done by simple capacitive compensator. Okay, So more on it in next class. I wish all the best to all of you. Thank you.